Hello everyone. So, we are discussing the thermal transmission related comfort of clothing. Now, in last segment we have discussed the thermal resistance under compression. So, this instrument which is actually its modification of the guarded hot plate, where at different compression level we have seen that the thermal transmission or thermal resistance changes. So, as the compression level increases, the thermal resistance of fabric reduces. So, here the values, resistance values are compared with the different other instruments like guarded hot plate and alum bata, and what we have seen, the present instrument gives the lower insulation. That means, for same fabric, which is mainly due to the higher initial pressure, and also we have seen that for same fabric, if we increase the normal pressure, so the insulation characteristics will be low. So, fiber will lose its insulation due to compression. That means, when the fabric is compressed, it actually releases the entrapped air. The entrapped air is lost. So, it actually lost its insulation characteristics. So, from this study we know that if we can now incorporate, on the other hand, if we can incorporate the air pocket inside the structure somehow, so we can incorporate the insulation, we can enhance the insulation of the fabric. So, with that idea, the next study, next approach was that how to increase the bulk. So, the by increasing the bulk, we can bulk in the yarn, we can make the fabric insulating. Bulk yarns are produced by technique that we will discuss. So, when we produce the bulk yarn, we convert the normal yarn to bulk yarn. So, we are introducing air pockets in yarn structure. So, still airs are entrapped and which affect the thermal transmission characteristics. So, if we entrap the air, say if we entrap the air in a cotton yarn somehow, in that the thermal conductivity will be reduced as compared to 100% cotton yarn. So, the entrapped air in the loose fibrous assembly, that space that do not allow the heat to transmit freely, okay, from the one layer to another layer. So, another approach was there to incorporate a bulk or incorporate an entrapped air, that is by micropores. We can incorporate micropores. So, this is done by actually blending the cotton fiber with PVA. So, PVA fiber, which is soluble in water, in warm water it gets dissolved. So, if we blend with a certain proportion the PVA fiber with the cotton fiber and produce a normal yarn, and after washing, after the fabric is made. So, if we can wash that fabric, that means PVA fiber within the yarn structure will come out. So, leaving micropores within the yarn, although there are micropores in staple yarn, but it will enhance the micropores. These micropores will actually enhance the thermal insulation characteristics. So, it increases the porosity of the yarn, increases the thermal insulation of the fabric. So, first we will discuss the mechanism of bulk development. That is a very common development, which is the bulk common principle, that is we use for acrylic bulk yarn. So, in acrylic bulk yarn production, what we do? We use two different types of fiber. One is a normal fiber and another is a shrinkable fiber. In present study, what we have used? We have used a normal fiber which is cotton, and the shrinkable fiber which we have used the shrinkable acrylic fiber. So, cotton and acrylic is blended. So, this is the blended yarn. So, where it is assumed that the yarn fibers are actually straight, fibers are, there is no crimp used, although these fibers are not actually straight, they are twisted condition, but there is no crimp, micro crimp present. But after the yarn is made, in the loose condition, in the hang form, these yarns are treated with the steam chamber. So, when at the heat chamber, when we treat this yarn, that may in that condition, the shrinkable acrylic actually shrinks. The total length of the yarn fiber, acrylic fiber gets reduced, leaving the cotton fiber buckled. So, cotton fiber gets buckled, and which forms the air pocket inside that. So, finally, we get the bulk yarn. So, bulk, we are incorporating the bulk air pocket inside the yarn. So, now let us see what are the effect. So, this is this curve, it is the bulky structure of weft yarn, because we have used this for this study. What we have used? We have used the 100% cotton yarn in warp, the normal yarn, and in weft yarn we have used this bulk yarn. So, this cotton bulk yarn in weft, it works as insulator. So, the x axis, this axis, this is the contour plot, where this x axis gives the yarn count at different count, that is 25, 30, 35 and 40, different count is there, and this is the acrylic proportion, that means shrinkable fiber proportion. So, here what we have observed, as we increase the acrylic fiber proportion within this limit, so 20 to say 40%, that within that limit, what we have observed, that bulk in the yarn increases. So, as the bulk in the yarn within this limit, it may not, this bulk increase, this trend may not be applicable if it is say 60% or 70%. At higher level, bulk enhancement of bulk may not be that much high, but within this experimental level, so 20 to 40% the bulk increase is there. So, this curve shows the thermal conductivity, and this is the thermal conductivity, and this curve is thermal conductivity, this is the thermal resistance. So, thermal resistance value is increasing with the increase in acrylic proportion. That means, the fabric gives the insulating characteristics of the fabric increases with the increase in bulk. So, the same fabric with the just by incorporating bulk in the yarn, we can enhance the insulation. Similarly, if we see the thermal conductivity value drops, just it is just opposite. The other trend we can see, that effect of yarn count, it is not that significant. Now, if we see the moisture vapor transmission, so moisture vapor transmission, if we see, it is with the increase in acrylic proportion, moisture vapor transmission increases, which is due to the creation of the pores which enhance the diffusion. So, due to higher and higher diffusion, due to the pore structure, it gives higher flow of moisture vapor. Now, try to see the microporous. So, microporous structure we have created, that we have already mentioned. The normal cotton fiber is blended with the PVA fiber, which is water soluble. So, after yarn is made, then we developed fabric, and after fabric is made, then when the fabric is washed, this creates the void space, and this void space are incorporating the insulation. This is still air is entrapped here, and this enhance the insulation of the fabric. Now, if we see, this is the air permeability. So, as the PVA content increases, the air permeability value, it is actually it is as the PVA value it is increasing, the air permeability is reducing. So, what does it mean? The yarn bulk is increasing. So, we have kept the total cotton content constant. So, total cotton content, if it is constant, total, that means total yarn diameter is more. So, which actually reduces the air permeability due to bulkiness of yarn, which means that internal pore that does not affect the air permeability. So, air moves through the interlacement between the yarn. So, if yarn diameter is more, keeping the yarn count same, so we will have the lower air permeability. So, irrespective of the fact that the yarn is pores. So, that shows that air normally does not flow through the pores, it flows through the surface of the yarn, that air opening between the yarn. So, although this yarn is bulky, so the yarn the air permeability is reduced, but we will see the opposite is the case of the in case of the moisture vapor transmission. So, the same with the increase, same trend, same with the increase in PVA content, the moisture vapor transmission will be just reverse, the moisture vapor transmission will increase. That is basically the phenomena of moisture vapor transmission is due to the diffusion mechanism, and here the air transmission is due to the opening through the in between the yarns. So, thermal conductivity, if we see, as we increase the PVA content, the yarn becomes bulky, the air pockets are there, and thermal conductivity is reduced. So, it is again it gives the insulation characteristics. So, we can use either the bulky approach or maybe microporous approach or maybe any other approach. By reducing the twist also we can make the yarn bulky. So, effectively the actual the finding is that if we make the yarn bulky, we can get insulation. So, yarn structure plays a direct role, a significant role in deciding the insulation characteristics of clothing. Now, see the moisture vapor transmission rate. So, with the increase in PVA content, we have seen that the air permeability reduces, but if we see here moisture vapor transmission, it increases significantly. So, that is due to, as we have mentioned, it is due to the diffusion characteristics. So, fiber with the yarn with the micropores, the due to the gradual transmission of moisture inside the pore, as soon as the vapor pressure increases in the pore, the moisture gets transmitted to other side. So, the more smaller pores are there, the higher will be the moisture vapor transmission. Our next study is in the similar line. Here what we have developed here, the hollow yarn, just to create here again the yarn structure is changed. Two types of yarns are produced, one is the twistless yarn. So, yarn does not, the fiber, it is a this is a twistless, means it is not made of the filament yarn, it is a staple yarn, it is a twistless cotton yarn we have developed, and also hollow cotton yarn, and it is compared with the normal yarn. So, and 3 different types of fabrics have been yarns have been developed, and from there we developed fabrics. Now, the warp which we have used, it is a 2-ply cotton ring spun yarn, it is a normal 2-ply cotton yarn is used. Fabric A, we have used a drape yarn with viscose, only viscose, it is a drape. 3 yarns have been produced, where core and sheath both are viscose. Okay. So, it is a 50-50 core sheath, and count here it is used 0.59 tex, sorry 59 tex. So, 59 tex yarn is produced. Type B yarn, it is again drape 3 yarn, but here what we have used, the core is viscose, okay, and sheath what we have used, it is a PVA which is washable. PVA viscose it is used, PVA viscose combination here, but core is viscose and PVA is at the sheath, and again the ratio here it is a 50-50 core sheath ratio, and its count it is a double, it is a coarser count, it is a in tex 118 tex, it is a just double to that of this. Similarly, the fabric or yarn type C, where it is just reversed, combination is reversed, core is PVA and sheath is viscose, 50-50 ratio, and again the yarn count it is a coarser, double to that of 100% viscose, it is 118. Now, what is the idea? Idea here is that the PVA is going to be washed away, and if we wash, and that is a 50%, and washing 50% PVA it is not commercially viable. One may ask, one may question about the validity of the or usability of this study. It is not, it is just for academic interest. We wanted to study the effect of the yarn structure on thermal transmission characteristics. So, here core viscose and sheath polyester, what does it mean? The sheath PVA 50%, if we wash, finally the after washing the linear density will be 59 tex. So, same 59 tex we are getting, but the structure here it is PVA, as PVA is in the core, that means the fabric B, the weft yarn will be the twistless, it is there is no twist, and the washing is done in fabric state after the interlacement is done. So, the fabric stage, if we cannot wash it in yarn stage, because if we wash, the yarn will be totally twistless and there will not be any strength. On the other hand, the fabric C, the type C is PVA in the core and in the surface it is a viscose. If we wash 50% viscose, again the count will be 59 tex, and the viscose as it is in the sheath, the core will be washed away, and the ultimately this yarn will be the hollow yarn. So, we have produced here the twistless yarn and hollow yarn, and it is produced in the fabric stage. So, this is the 2-ply yarn, here both it is a fabric A, grey fabric A, in the weft warp is 2-ply cotton yarn, weft we are using both viscose, although it is showing 2 different colors, but it is a viscose and viscose. So, when you wash the fabric, nothing will happen. So, this structure will remain, it is 100% viscose. Then again this as a PVA sample B, its warp is 2-ply grey yarn, and PVA is at the sheath, viscous is at the core, purple color, this green color sheath will wash out and the ultimately this core will remain, which is twistless. And here it is just reverse. Okay. This will get this is the PVA, purple color, this will be washed away and ultimately we will get a hollow yarn. Now, try to see the characteristics. Now, viscous in core sheath, the yarn count we are getting after washing 59 takes standard yarn count. So, this is the nominal count 59 takes, it may actually vary little bit. Fabric ends per inch, peaks per inch after wash we are getting almost a very close value. So, there after wash the fabric mass is almost same, and thickness, if we see thickness here where it is a hollow yarn is used, thickness is little bit high. This is due to the presence of hollow yarn. And if we see the air permeability, what is happening? Air permeability in fabric A and fabric B, they are on the higher side. Okay. So, this is the air permeability, but fabric C has got very less air permeability because of the bulky nature. So, ends per inch, peaks per inch, fabric set is same. So, due to its higher diameter, again it is blocking the pores between the opening space between the yarn, although this yarn has got higher pore inside the core. So, this C fabric gives lower air permeability. And if we see the thermal resistance value, thermal resistance in TOG it is measured of the fabric. So, fabric A gives least thermal resistance, followed by fabric B, and fabric C is giving highest thermal resistance. So, that means the fabric A due to its compact structure it gives least thermal resistance, highest thermal resistance is given by the hollow yarn. So, due to the openings that is the hollow air entrapment. Water vapor permeability, it is interesting that water vapor permeability is highest in case of the hollow yarn. So, that hollow yarn gives least air permeability, but it gives highest water vapor permeability. That means, this can be used to those condition where it's because it requires a higher air permeability, water vapor permeability with least air permeability. If you see the wicking characteristics, the liquid transmission characteristics, this where the twistless yarn, the B gives maximum wicking characteristics, particularly in wave direction, because this is due to the arrangement of fiber, the alignment of fiber towards the wave direction, which creates the clear pore, clear capillary, and which helps the increase in wicking characteristics. But the fabric with normal drape yarn, random structure, which gives least wicking characteristics. And water absorbency, it is a very high water absorbency for in case of hollow yarn, which is due to the fact that it contains a large pore inside the structure and gives the higher water absorption. It can hold the more and more water inside the structure. So, the observations are, apart from the type of fiber, fabric structure and fabric finishes, the structure of yarn also plays an important role. So, we can control the thermal comfort by type of fiber, by fabric structure, by fabric finishes also, but thermal comfort can be controlled to a large extent by controlling the yarn structure. by incorporating the bulk in the yarn structure. So, fabric with twistless fibrous assembly shows higher air permeability, lower thermal resistance, lower water vapor permeability, higher wickability, lower water absorbency than the fabric with hollow fibrous assembly. So, depending on the requirement we can select the yarn structure, whether should we go for the hollow yarn or should we go for the twistless yarn or normal yarn, that depends on the our requirement, what type of air permeability we require, what type of thermal resistance we require, what type of moisture vapor permeability we required, wickability we require. So, absorbency. So, these are our requirement and accordingly we can select our yarn structure. Now, the next observation is that effect of fiber yarn fineness and hairiness on thermal characteristics of fabric. So, if we use the finer yarn, so that will give us the lesser thickness of fabric, and lesser thickness will give the less thermal resistance. And also if we increase the yarn twist, so that means if we increase the yarn twist, it will the entrapped air within the structure will reduce, that ultimately will give less thermal resistance, and also the fabric thickness will reduce. So, less higher twist always give less thermal resistance, that is due to the different factors. One is it removes the entrapped air. So, entrapped air content is reduced. So, the conductive thermal transmission is reduced, and also with the increase in twist the diameter of yarn reduces. That means, for same set fabric set, same ends per inch, peaks per inch, for same mass per unit area, the openness in the that is cover factor of the fabric will reduce. So, that will enhance the radiative and convective heat loss. So, both all convective, radiative and conductive heat is lost due to increase in twist. So, increase in twist has got the major impact on thermal transmission characteristics. So, another parameter, another factor which affect the thermal resistance of fabric, it is a hairiness. If we can increase the hairiness of yarn or yarn fabric surface hairiness, we can enhance the entrapment of air, still air in the surface of the fabric. So, that is how that if we normally try to increase the thermal insulation by brushing at the surface. So, that it prevents the heat flow, that entrapped air at the surface prevents the free heat flow, and which results higher thermal resistance. Now, another factor, it is the effect of microclimate thickness. So, what is that? The microclimate, as we know, that it is between our body, our skin and the cloth. So, depending on the microclimate thickness, our insulation, the thermal insulation changes of clothing changes. So, what is microclimate? It is basically still air, entrapped air. Okay. The increase in microclimate thickness increases the thickness of air layer between the skin and fabric. So, total heat flux of human body decreases. So, from our skin to the environment, that total heat flux will reduce due to the entrapped air, but this effect of thickness is less than the effect of microclimate. So, we can increase the fabric thickness to reduce the heat flow, or we can increase the microclimate thickness to reduce the heat flow. So, if we compare these two, the effect is more in case of microclimate thickness. So, we have if we have two options, if we can increase the microclimate thickness, if we can increase the entrapped air between skin or fabric or within two layers, between two layers of fabric, that option we should take other than that increasing the fabric thickness. We should not make the fabric thicker unnecessarily if we can incorporate, if we can develop a structure with higher microclimate thickness. So, that effect of microclimate thickness is more prominent than effect of fabric thickness. So, because the fabric consists of fiber, fiber has got some thermal conductivity and the thermal conductivity of fiber is more than air. So, if we can incorporate pure air inside the structure, that will be preferable, and fabric thickness, the effect of fabric thickness is larger when microclimate thickness is less. So, if there is no microclimate or very thin microclimate, then we can have the clear effect of fabric thickness, but if the microclimate thickness is large, then changing the fabric thickness will not affect the thermal insulation characteristics of clothing. So, here we are talking about the clothing ensemble, where we can incorporate the microclimate between the skin and clothing or between different clothing layer. So, we will see in our one of the studies, next we will see the how incorporation of air layer between two fabrics layer affect the thermal transmission characteristics, thermal insulation characteristics. So, that thermal transmission through different air gap with different convective mode. So, that study here three layers of fabrics have been taken, outer layer, middle layer and inner layer. Between these three layers we have actually that we have incorporated the air layer, and thickness of air layers have been changed to just to see the effect of the microclimate thickness, keeping the fabric layers same. So, this is the arrangement what has been done. It is a outer layer fabric, middle layer fabric and inner layer. Between these layers, outer layer and inner layer, middle layer, we have incorporated air gaps, and between middle and inner layer another air gap, two sets of air gaps are there. So, the experimental design was such that between inner layer and middle layer, the air gap distance have been changed from 0 millimeter, that is there is no air gap, to maximum 7 millimeter. So, this is these are the combination. So, air gap, the fabric combination 1 means there is no air gap between inner to middle and middle to, this is the air gap 2, air gap 1. Okay. So, and next fabric 2 sample, when the inner and middle layer there is no air gap, but middle and top layer there is air gap of 2. So, in this way it is changed. So, if we see this fabric final, this fabric is that first, second, third, fourth, fifth, sixth, seventh, eighth fabric, if you see the total thickness of the assembly will be 14 millimeter plus the thickness of inner layer, thickness of middle layer and thickness of outer layer. So, this is the experimental design has been made with to have different types of fabric layers with different air gaps. Now, this fabric layers are of different type, like A fabric assembly So, this fabric assembly we have developed 5 fabric assemblies A1, A2, A3, A4, A5. The assembly 1 where its inner layer is woven fabric. So, for all the inner layer we have used the same woven fabric. So, same woven fabric is used for all the fabric layers. Layer 2 middle layer we have used, actually we have used 2 different types of fabrics. One is non-woven wadding, non-woven fabric, and another is the warp knitted spacer fabric. So, the idea of middle layer is to provide the insulation. So, it was thought that okay, that non-woven fabric is used to give the it has it is porous in structure. So, that is why non-woven fabric is used, it entrap large amount of air also, and warp knitted spacer fabric which also entrap large quantity of air. So, this with this combination it is thought, but finally what we found that non-woven fabric gives better insulation than warp knitted fabric spacer fabric, because the orientation of the spacer yarns which are vertical. So, spacer yarns orientation which helps in flow transmission of heat. So, that it gives lower thermal insulation. And outer layer we have got 2 types of outer layer, one is normal woven fabric. So, for fabric A1, A2, A3 we have used normal woven fabric, and A4 and A5 this gives the coated fabric. So, coated fabrics with different known pore size, it is basically it is with very less pore size which only allows the moisture vapor to transmit, it is water impermeable, moisture vapor permeable fabric. So, these 5 combinations have been made, then we have measured the thermal and moisture vapor transmission. So, this is actually measured in sweating guarded hot plate. So, guarded hot plate where this is a test plate, bottom plate, fabric specimen is there and its top plate is placed. Now, here the fabrics, it is from different types of fabrics are there. So, what we have done, the total thickness of fabric. So, total thickness is changed. So, this is the minimum thickness and this is the maximum thickness, but the combination is the same fabric combinations are there. Okay. These are the same for assembly 1. What is the assembly 1? This is the assembly 1. Assembly A1 it is a woven fabric, then non-woven wadding and woven fabric. So, which is assembly 1, and the thickness is changed, thickness of total assembly is changed from 0 to 7. So, fabric, that is the air gap is changed. So, this is the total thickness, it goes up to say 20 or like that 20 around say 17, 18 millimeter thickness, and thermal resistance is given. So, what we have observed, with the increase in thickness of the air gap, thermal resistance for all conditions, a condition of mode of transmission, it is increasing. So, what are the modes? Here there are 3 different modes have been used. One is non-convective mode, next is that blue one is non-convective mode, red one is that natural convection, and third one this is it is a forced convection. Now, what is non-convective mode? Non-convective mode is where we place top plate. So, we do not allow any convection. So, without any convection, how much heat is transmitted. So, that is the non-convective mode, and when we want to measure the convective natural convective mode, then top plate is removed. So, actually the heat is allowed to flow in convective mode also. This is the natural convection with the natural convection also, and forced convection, that system is that where we have to remove the top plate and allow the air to flow at certain speed. So, that it actually simulates the wind chilled condition when air is blowing. So, air is then, and in y axis it shows the that thermal resistance. So, thermal resistance at different convective mode is actually it is showing. So, what does it show? This picture, this graph, this is for assembly 1 and this one is for assembly 2. Assembly 1 and assembly 2 are almost same, only that, and here the top layer we have to see what is the top layer. Top layer here we have used it is a woven fabric, we can see here it is a woven fabric. Both assembly 1 and assembly 2 their combinations are same, only the non-woven wadding this fabric their thickness, their mass per unit area is changed. So, here if we see the non-convective mode, the thermal resistance is highest. So, there is no convection, that is why it gives the highest thermal resistance. And if we see the natural convection, through natural convection little bit heat is transmitted, extra heat is transmitted, that is the although the difference is less, but still this difference shows the how much air, how much heat is transmitted through actually convective mode. So, natural convection. So, the difference is showing the amount of heat transmitted in by natural convection. Now, when air is started blowing, what is happening? Total phenomena has changed, total principle has changed. Here it takes away the air from that portion and total forced convection is started. So, when forced convection started, that means air started blowing, the thermal resistance of the total system drops drastically. It is a significant drop, sometimes it becomes half thermal resistance. The total system is actually the thermal resistance of the total system, total clothing system is dropped to almost half, most of the cases, huge drop in thermal resistance. So, that means the forced convection for assembly 1 and assembly 2 are significant. So, that is how it is showing that with the increase in air entrapment, the thermal resistance is increasing and it shows the non-convective thermal resistance is highest, followed by the natural convective thermal resistance, and in forced convective mode the thermal resistance is lowest. Now, if we see the fabric assembly 5, what is fabric assembly 5? Fabric assembly 5 shows that it is the top layer is changed with the coated fabric. So, this is the coated fabric. So, in coated fabric the pores are almost blocked. So, whatever air is moving, that does not affect the heat transmission, convective heat transmission characteristics. It is almost close to non-convective mode or natural convection. So, there is no difference. It is the fabric, when if we are using a breathable layer outside. So, that in that case the thermal resistance it can retain the thermal resistance. So, that is how in case of wind chilled condition. So, when cold air is blowing, so in those application we must use a clothing outer layer with a coated outer layer. So, here the outer coated layer its use is not only for the waterproofing and other, it also prevents the heat loss due to the forced convection. So, that is this curve shows here. So, higher thermal resistance at non-convective mode, less thermal resistance at forced convection. Breathable and metallic coated fabric improves the thermal insulation property at forced convection mode. So, we must use some breathable and layer to prevent any heat loss. So, higher thermal resistance for nonwoven fabric is that is more than it is a spacer fabric. So, thermal resistance in nonwoven fabric it is more than the spacer fabric. If you see the quantity of thermal resistance at any level, so it is a lower than this is the fabric with the spacer fabric. So, assembly 3 if we see it is a with the warp knitted spacer fabric, and if we see the value here, this is the spacer fabric, here typically it is a 0.1 less than 0.1 typically 0.2, here 0.2 to 0.3. Okay. So, that overall it has been observed that the spacer fabric instead of what we thought that it will provide the insulation, it is not able to provide insulation. The reason behind is that it is a due to the arrangement of spacer yarn. So, for extreme cold climate clothing to make our body warm, so to enhance the thermal resistance, it is not recommended that spacer fabric is not recommended. So, in place of spacer fabric one can use the nonwoven wadding. So, this also it is assembly 1 which is thermal resistance of nonwoven fabric, we can see the effectively its total value is more than the spacer fabric. So, here we have discussed the thermal transmission characteristics through different air gap and different convective mode. So, in the next segment we will study different process parameters which affect the thermal properties of clothing. So, here we have developed different fabrics, nonwoven fabrics and different combinations of nonwoven fabrics and effect of our needle punch density, effect of mass per unit area, effect of depth of penetration on thermal transmission and moisture vapor transmission of clothing, which actually affect the thermal comfort characteristics. So, this thing will will discuss in our next segment. Till then, thank you.